Hey everybody, welcome back. Today we are going to be doing an overview of machine learning. Now this is going to be kind of a high level take on machine learning. We're not really going to be going deep into any of the different algorithms that are out there. Machine learning is a very deep field that you can fall into. We're mainly going to be looking at it obviously from the cloud perspective and how we can use some of the existing tools that are out there for our purposes. And this is really a what is machine learning, right? If you want to go deep down the machine learning rabbit hole, there are a ton of algorithms out there. There is a lot of different aspects that you can focus on. Really, what it means is you have to get pretty good at matrix math, is what it boils down to. But we are again going to be looking at this from a high level. Now I've got it's a Google Slides kind of day. So, what we're going to be basically focusing on here is what is machine learning and how can we bend it to our will. Now, what machine learning actually is, and it seems like there's a lot of, hullabaloo about it. Basically, we're just making decisions based on known data that we have. We're looking to the past. I guess depending on the algorithm, some of them don't necessarily need historical data, but we're mainly going to be trying to make predictions with it. We are going to try and figure out the best decisions possible. And you might be asking, what kind of decisions? Well, maybe if you want to suggest Netflix shows, maybe you want to suggest a route on a map. Um, Basically, anything where we can kind of offload a decision-making strategy to an algorithm, and where we feel safe and comfortable doing that. That's where machine learning would fit in. And what you see here on the slide in front of you, typically they're made up of a lot of data, an algorithm, some sort of an insight, and then a decision at the end. And basically what's going on here is that you feed an algorithm data, you train it, you kind of finesse the model, you finesse the algorithm into whichever kinds of decisions you want it to make, and then you start applying it to new data, and that will give you your decision. And you can use this in multiple ways. Again, I mentioned maps before. So let's say that we have, a route that's been planned for you using something like Google Maps or Bing Maps or whichever your favorite mapping software of choices. And maybe, you want to take the quickest route home, you want to take the most scenic route home, you want to avoid as much traffic as possible. Machine learning can be used based on data that it currently sees to generate that decision. Or maybe it's not even, mapping, maybe it's estimating taxes, right? Based on past historical data, we can figure out how much taxes we're going to owe every year. Now, how do we get this information, right? How do we actually get an algorithm to do this? Well, first and foremost, we need data. So at the core of a machine learning algorithm, typically there is a model of some kind. And this model, it's generally a very pliable construct. So you have, and again, I'm glossing over a ton of details here, but you have a black box model. We'll call it, a thing basically. The decision making inside of this thing or this model basically is constructed of a series of pathways, a series of weights. And you can go down like the neural networking route, you can go down uh, recurrent networks. I mean, deep learning, there's a lot of different ways you can set up models. At the core, they all tend to be neural network-ish, but basically they're flexible. They can learn over time. And if I feed in a certain piece of data, it's going to be routed and transformed and along this model until you get an output, which is your decision. Another example would be taking robotics, for instance, and training a controller to make decisions. So if you have a very simple, say, a Roomba, and you're feeding it data, an analytical or a decision engine, a machine learning engine would take in all these inputs and it would determine, okay, activate a rotation or activate forward motion in the motor because This is the data that we have. This is what we've has worked for us in the past. So if we are giving this analytical engine, I keep calling it analytical, this machine learning engine past data, well, this is going to be examples. All right, so if we want tax predictions, we need prior tax filings. If we want reliable trip information, we need past reliable trip examples. And some of these might be good, some of them might be bad, right? We are basically giving our model data to act upon, and we can go through and label them if it is a good example, if it is a bad example, do this, do not do this, and that will eventually train this model to make decisions. So this is typically referred to as a training set, depending on your strategy. Some of this can be supervised, it can be unsupervised, but basically we are training a model. Now here is an example where we are basically trying to train a model to recognize either good or fractured polygons of some type. All right, so here we have a data set that we are putting into an algorithm to basically train the model. Here is a list of good entities. Here is a list of fractured entities. And based on what we're doing, you know, with our model, it's going to learn, okay, anything with a line through it, kind of like this blank negative space, is probably a fractured object, whereas the rest of them are quote unquote good. Now, these labels are something that you, as the designer, would typically apply to the training set. That can be a very intense and time-consuming task, just to let you know. But this is one of the ways that we teach models and we train models. In this algorithm step here, this is actually kind of interesting because this can be a standardized algorithm, right? So if we're doing image recognition, we could apply the exact same algorithm to understanding this versus, say, understanding if a part on a assembly line for putting cars together is bad or good. Interestingly, it is the same algorithm, but we are feeding it data that we, as humans, typically have labeled. The algorithm is going to understand this is good, this is bad. The image recognition part is standardized. It's going to spit out a trained model. And kind of the goal here then is to take some new data and apply it to your trained model and then get a decision based on that. So whereas here we have past examples where we know this is good, this is fractured, here we're going to send in something completely new to the model. It has never seen, say, a triangle before. And we feed this into our model, and it's going to spit out, is it good or is it fractured? And ideally, this model will say, yes, it is good. We don't see any negative space in this thing. Now, does that mean that we're going to get perfect information out of a trained model? No, there is not a guarantee. And it's based on what you feed it. Your decisions are only as good as the data that comes into it. It is possible that we have, in this very simplistic, contrived example, maybe we have a fractured object that is actually good. Or maybe we have a concave object of some kind that it recognizes as fractured instead of all these nice little convex style polygons. Basically, though, the key is that you should try and train it as well as possible. Now, it is possible to overtrain where it just only recognizes what you feed it. Deeper discussion for another day. But kind of the interesting thing to talk about here is at the high level, let's say we have fed it data. I mentioned the algorithm is standardized. So if we have a task to do, and again, it doesn't have to be image recognition, it can be predictions, it can be transcribing speech to text in like these examples that we see here. These algorithms are standardized, meaning that we don't care what the image is. We don't care what the time series is. Maybe we don't care what language somebody is speaking. Basically, these algorithms will work regardless. It's the data that you are feeding into it, which will customize things. So if you wanted to say do image recognition or, image categorization, something kind of like this, the algorithm isn't going to change. The data will change, but this is standard. You could just grab this off of GitHub or open source repository of choice and stick it into your machine learning algorithm, and it will understand it regardless, which is kind of nice. So, let's say that we have image classification is a task that we have to do. And again, classification is just applying a label to an image. What is this thing? Think of any of those Google, or not necessarily Google, but like those robot protection services. Pick the bridge in this image or pick the mountains. Basically, you're training um, other people's machine learning algorithms with this image classification here. So I provide an image into a trained ResNet model. So ResNet's one of the standard image classification algorithms. We can get classes out of this. And interestingly, when we are here in the cloud, um, a lot of these things are kind of selectable at a very high level, and we'll do some examples with these. So this is just kind of more of an example of how we can use the same algorithm for different data sets. Right, so here we have circles and triangles. Here we have squares and hexagons. Um, this standard ResNet algorithm that we're using will yield a trained ResNet model. Again, the data sets are different, but it's still kind of the same idea here in red. Now, if I feed a circle into this model, there is a chance that it doesn't know what to do with it because maybe it never saw a circle before and it just has to make an educated guess. Again, it just kind of depends on the fidelity of your training set. Um, yeah, so here this is basically more of the same, just a different set of training models. So here we're trying to recognize maybe water-based plants. So here we have lily pads. We have trained our model with prior examples of vegetation in the water. Give it seaweed, give it lilies, give it basically anything that can exist in water, right? Our trained model should spit out that this is X image. Whereas here, we are looking at fractured polygons. If I put water lilies into this model, it's not going to work. Algorithm didn't change, but the model changes. Just kind of a key to consider. And why are we talking about this? Well, a lot of these tasks can be reused and repurposed, which is kind of interesting. The logic doesn't change. The process doesn't change. The algorithm doesn't change. The only thing that changes is your model, your training set, which the algorithm takes in, trains a model. Now you have a model that can be used for X task. So, what kind of data do we need? Again, we need high quality, good, well labeled, well described data. And you typically need a decent amount of it as well, right? Because we are training this model over time. We are basically trying to figure out, okay, if I see something new, is there any piece of this new thing that I can recognize from past examples? And if I don't have any way I can liken something new that I see to past information, I'm gonna have a really hard time making a correct decision. So examples of positive cases and negative cases are very, very helpful. This is a good condition part. This is a fractured part. This is a part with a scratch on it. This is actually a lily that is not in the water, for example. So you need basically all kinds of different examples. One of the very common questions that you may ask if you are not a machine learning person is where does it fit in with all of these other buzzwordy terms we've heard, right? Artificial intelligence, deep learning, neural networks, recurrent networks, all of these different things that we probably have heard about from, technical press or things like that. What is the relationship? Well, this figure here is kind of a nice little example where let's say that we have something called deep learning. And to me, deep learning is just a very fancy way of saying neural networks. different flavors of them, obviously, but basically we are simulating a brain effectively with a bunch of pathways and transfer functions and neurons and all kinds of fun stuff. Separate topic. Machine learning relies on these set of algorithms to actually do its job, right? It is basically just a tool set where you can use some algorithm to make predictive decisions, right? So machine learning is going to take this kernel of an algorithm here. Maybe it's not deep learning, maybe it's something a little bit simpler. We can swap out the algorithm and still enable machine learning, I should say. But this is very common for, say, structured and unstructured data, images, all that kind of fun stuff, all subsumed by deep learning. Machine learning is going to be making predictive decisions based on that. Artificial intelligence, on the other hand, takes it a step further, enables devices, enables controllers, enables programs to basically think for themselves. So here with machine learning, we are making the predictions. Adding on something like AI would be automatically taking those decisions and implementing them. So just to kind of contextualize where we are at here.